Welcome back to the course of chemical crystallography. In the previous lecture, we were discussing about the 32 point groups and we have learned how to draw the stereographic projections of various point groups, starting with simple point groups, and we ended up drawing the point group 2, 3 as you can see on the last part of the previous lecture. So today we are going to start talking about the crystallographic space groups. As we have already indicated, there are 230 crystallographic space groups, and these space groups are the only ways in which the objects can be arranged in 3 dimensions following the translational symmetry and all other possible crystallographic symmetry elements. It incorporates all the 7 crystal systems and utilizes the lattice centering of Bravais lattice and incorporates the special crystallographic symmetry elements like different varieties of screw axes, glide planes, and so on. So if you can concentrate here on the table, we have categorized or classified these crystallographic space groups in different types of lattices. Here we have under Triclinic 2 space groups which are only P1 and P1 bar, which means the first letter P stands for primitive and 1 or 1 bar stands for the corresponding symmetry that is present in that. So 1 means there is no symmetry, and 1 bar, as we already know, means the inversion center. The next higher symmetry crystal system is monoclinic. Under monoclinic, there are 13 space groups possible with different lattice settings. I have given some representative examples here: P2, PM, PC, P21 by M, C2, C2 by C. These are examples of monoclinic space groups with various symmetry elements present. See, there are 2 types of lattices possible in monoclinic, primitive and C-centered. So I have chosen both primitive and C-centered lattices as representative examples. In case of monoclinic, there can be centrosymmetric and non-centrosymmetric space groups. The non-centrosymmetric space groups are P2, PM, PC, C2, etc., where you do not have center of inversion I. Whereas in case of P21 by M or P2 by M or C2 by C, where we have a combination of two-fold and a perpendicular mirror, it results into a centrosymmetric lattice or centrosymmetric crystal structure. The next higher symmetry is orthorhombic. You can see under orthorhombic there are large number of space group possibilities, simply because in case of orthorhombic you have both primitive, body-centered, face-centered, and one of the faces-centered lattices possible. So all 4 types of Bravais lattices are possible for orthorhombic system. And then in orthorhombic system you can see the symmetry elements are 3 in number. The first symmetry element that we see, if it is one axis, whether it is a simple axis or a screw axis, that first symmetry element signifies either if it is an axis, it is parallel to x-axis. If it is a mirror plane, it is perpendicular to x-axis. So when we say, for example, a space group PCA21, it means it is a primitive lattice having a C glide perpendicular to x, an A glide perpendicular to y, and a 2-1 screw parallel to z. So in the same manner, if we think about the space group IMMA, it indicates that this is a body-centered lattice, which means I. The first M is a mirror plane perpendicular to A or perpendicular to x. The second mirror is perpendicular to y, and then the third one is a glide plane. It is A glide perpendicular to C. So accordingly, we should then try to generate the symmetry equivalent points for these space groups. Once again, among these, there are some space groups which are non-centrosymmetric, for example, P2121, P222, FDD2. These are non-centrosymmetric space groups, whereas PMMM, PBCA, IBCA, FDDD, these are IMMA, these are all centrosymmetric space groups. The next higher symmetry crystal system is tetragonal. As we have seen in the previous lecture, the tetragonal system has a large number of possibilities of point groups. As a result, it has the largest number of space groups that belong to tetragonal system. And once again, here you see that it can be P4, P4 bar, I4, because in tetragonal you can have primitive and body centered lattice, and you can have point groups either 4 or 4 by M or 4 by MMM. So there are tetragonal space groups like these as well. So when we see P4, this means it is primitive and you have a 4-fold axis parallel to Z. When we say P4 by M or I4 by M, it means you have a 4-fold axis along Z and a mirror perpendicular to that 4-fold axis. That means it is perpendicular to Z. The P and I, as usual, signifies primitive and body centered lattices. When we look at the space groups like P422, I4122, it means there are other symmetry elements other than just the 4 which is parallel to Z. So in case of P4222, in that case you have a 4-fold parallel to Z, you have a 2-fold parallel to X, another 2-fold parallel to Y. Similarly, when we talk about I4121, it means I have body centered lattice, 4-1 is parallel to Z, and I have a 2-fold here and a 2-fold in the Y axis. So both X and Y are having two-fold, in this here to the 2-fold axis, right? So when we go to trigonal system, we have 25. In case of hexagonal system, we have another 27. The distinction between trigonal and hexagonal, you can see that in case of trigonal system, the highest symmetry is 3-fold, while in case of hexagonal, the highest symmetry is 6-fold. So by looking at 3 or 6, we should be able to distinguish whether it is a trigonal lattice or a hexagonal lattice. And you see, in the previous class, we tried to distinguish between P3M1 and P31M in 2-dimensional lattice, and here in case of trigonal, we have similar situations. The final is cubic, under which you have 36 point space groups, and they are designated as P432, I432. Remember, these are just representative examples. I have not listed all the space groups. So here what we need to do is we need to go to any standard textbook and look at the table which indicates all the possible space groups that are there in crystallography, and try to understand why one space group belongs to cubic and not tetragonal or hexagonal, and so on. So at this point, what we need to understand how to write these space groups. If you have noticed by now, all the letters that I have written, all the letters that are written here, like P in all the cases, MMM, DDD, CA with P. So all the letters that we are writing, those letters are all written in italics, and the numbers that we have are non-italics in nature. So while representing these space groups using any document using Word or PowerPoint, one should use these notations The space groups, wherever you have letters identifying the lattice centering or any symmetry element like mirror or glide, those letters are written in italics, and the numbers, that is this axis 2, 3, 4, 4, 1, 2, 1, 6, 6, 3, whatever, are written in normal font. At this point, I would like to also indicate that the crystallographic space groups can be subdivided into few ways. These space groups can be divided into two major divisions: centric or centrosymmetric and non-centric or non-centrosymmetric space groups. Centric space groups will have inversion center I and it will not have inversion center I. But then there are point groups which do not have I but can have a mirror plane. For example, PM, PC, CC, these are non-centrosymmetric. Similarly, P2, P2121, P222, they are also non-centrosymmetric but without mirror planes. So the non-centric space groups can be subdivided into again two different subclasses: achiral and chiral. Achiral space groups may contain a mirror or a glide in them, and chiral space groups will not contain any mirror or glide. So the example of non-centrosymmetric but achiral space groups are PM, PC, CC, PCA21, P4MM that are present here. But then the chiral space groups are P1, P2, P21, P2121, and so on, which do not have any mirror plane in them. The importance of these chiral space groups are that all chiral compounds will end up crystallizing in these chiral space groups. In general, these chiral space groups, the number of crystals that we find crystallizing in different space groups, the occurrence of chiral space group is very less because mostly the chiral compounds adopt these chiral space groups. All other molecules which are not chiral, they can adopt centric or non-centrosymmetric space groups which are achiral in nature. So now, since we have talked about these crystallographic space groups, I would like to now show you how to draw these space groups in two-dimensional representation the way we were doing it for 32 point groups. So I'll take some simple examples. I'll restrict myself mostly towards triclinic, monoclinic, and we will do one or two orthorhombic towards the end of the next lecture. So now we will try to see how these simple space groups can be represented in a two-dimensional figure. So the first space group that we know is P1, which is primitive and there is only one symmetry, that is one-fold rotational axis of symmetry. So this appears in case of triclinic lattice. And as you know, the triclinic lattice is nothing but A not equal to B not equal to C, angles are not equal to 90 degrees. So I have drawn a projection of oblique lattice with the O, B and A as a projection, plane of projection. And now if I put one object with a plus sign which indicates that this object is somewhere inside the unit cell and the projection is falling on the two-dimensional board, plus sign indicates that the object is above the plane of projection. Since there is no other symmetry element, if I just draw the translational symmetry related objects outside this unit cell, it will complete the representation of P1 space group. The next higher symmetry is P1 bar, which means it has a center of inversion. So once again, if I draw oblique lattice, I am not going to do anything wrong, because in case of triclinic, the angles are not 90 and hence we can draw oblique lattice. So just like before, like P1, I am drawing the symmetry related objects first, which is the translational symmetry that is there in P1, and now when we say that it is bar, the center of inversion that we have comes at the corners of the unit cell, as I am marking it as red. So the inversion related object, if this was your unit cell, if the object is here and it is inverted against a particular origin, it goes to the lower unit cell. That means it goes below the plane of projection. So as soon as something goes below the plane of projection, we draw it with a minus sign. So now we place the inversion related object for all the points that we have drawn with minus sign on it. This represents the P1 bar. Now you see what has happened. Because of the symmetry related molecule here, the original molecule which is at the first point and the newly generated object, there is a center of inversion at the center of this face. There is an inversion center here. So these are the inversion centers which got generated at the centers of all those faces and at the center of the body. So now if we try to write down what are the equivalent points present in these two lattices. In case of P1, you have only one object or only one molecule present in the unit cell, so it has only one equivalent point x, y, z. But in this case, if you see, there are two such atoms, and these two are numbered as 1 and 2. So the point number 1 represents x, y, z, and point number 2 represents x bar, y bar, z bar. So this point number 2, which is here, can be translated inside the lattice by doing one unit translation along B and then one unit translation along A. So if we add 1 to y bar and 1 to z bar, we end up getting the lattice, the point inside the lattice, and it is still x bar, y bar, z bar with respect to a different center of inversion. So the next lattice that we would like to see is P2. In case of P2, it is primitive and it has a twofold axis of rotation, and I am now drawing the AB face as the plane of projection, and I am taking my object inside the unit cell as plus. When I am saying P2, this twofold is along the unique axis B, which means the twofold is here. So now if we do a twofold, this is my cube, I have object here and the twofold is somewhere there. So if I do a twofold with this object, it goes to the lower unit cell. So when it goes to the lower unit cell, that means it goes to the plane below the plane of projection, the two symmetry related object should be written as a minus. Now I would like to draw these objects with their corresponding translational symmetry. In all the four places, and what we now see is that a new twofold is generated in the middle of the unit cell. So this is the representation of P2 space group, and now we have 2 points 1 and 2 as the equivalent points. This point 2 can be moved inside the lattice by adding 1 along A. So the equivalent points should be x, y, z, and the second point is a twofold about the y axis. That means it should become x bar, y, z bar, because y is the unique axis about which it is rotating. So the coordinates of x and y x and z should change the sign and generate the two equivalent points. So here we have one equivalent point in case of P1. In case of P1 bar, we have two equivalent points. It is centrosymmetric. Here we have two equivalent points, but it is non-centrosymmetric. How do we know it is non-centrosymmetric? Because we have two coordinates x, y, z and x bar, y bar, z bar, x bar, y, z bar, they are not related by inversion symmetry. The next point group that we would like to draw is PM. P again means primitive and M is a mirror, and since it is a monoclinic space group, this mirror is by convention perpendicular to twofold. So once again I will draw a rectangular lattice and it is like represented as origin here, B and A. Now I am placing my object at one point here and drawing the corresponding symmetry related objects in the adjacent unit cells. Now as I said, the mirror is perpendicular to B, that means the mirror is along A. This red line is the mirror. So, if you apply mirror symmetry, what happens? If the object is here, your mirror is here, it gets reflected like that, but it still stays above the plane of projection. So, I am doing a mirror image, but with a plus sign. So, when we look at this representation, what we find is that there is a mirror plane generated through the midpoint of this unit cell. So, if the first point is 1, the mirror image is 2, the point number 2 is moved inside the lattice by adding 1 unit along B. So, the equivalent points for these are x, y, z, and for the second point it is x, y bar, z, because the mirror is perpendicular to y. And once again we see that there are 2 lattice points in this unit cell. So, whenever we are identifying these number of lattice points, these number of lattice points are designated by a number called z. We will see that this number z is highly significant when we are trying to identify a particular unit cell from X-ray diffraction data, and we are trying to calculate some parameters to see whether the unit cell that we are getting can fit our molecule or not. So, to do that we need a knowledge of this value z for every possible space groups that we can think of for the data that we are getting. So, in this today's lecture we have learnt about the space groups. We have understood how the space groups should be represented. If a space group is written, how to understand what kind of crystal system, what kind of symmetry elements that are present in that space group, and then we should be able to now identify a centrosymmetric and a non-centrosymmetric space group. We should be able to identify a chiral and achiral space group, and now I have just taught you how to draw these projections of these space groups in 2 dimensions. These drawings are there in International Table of Crystallography, volume A, with a similar notations present in that. So, in the following class we will continue learning these projections for other space groups, because some of them are bit complicated. Just if you see the diagram or drawing, you may not be able to draw it yourself, and that is why we need to do it during the lecture hours, and I would like you to practice it at home.